You can see I'm just following this along in units of grams per meter per square meter. It's net production in terms of grams per square meter per year, while the biomass of plankton in a lake could be expressed as grams per liter. It's net production as this. Don't get too hung up on these units. Those are more important later on if you're going to do a conversion analysis, but they'll give you those, or I will give you those if the thing is, the main takeaway on this video is to see the difference of these two. So autotrophs carry out primary production through photosynthesis. These are photoautotrophs, or by deriving energy from inorganic molecules, which are chemoautotrophs. And then production in heterotrophs is termed secondary production. That's a key term to remember. So this is primary production versus secondary production, where energy. All right. And then here is a couple of just a couple more concepts in this video. The relationship here for this would be such and such. The relationship would be biomass and bioproduction during a particular time can be the new biomass equals the existing biomass. All right. In other words, how much you started with minus the biomass change. So this would be the new biomass that would be created. So that kind of stands to reason, I think. And then the second law tells us that organisms cannot be 100% efficient in assimilating the energy they consume. There is an unavoidable loss of energy as heat. So the significance of this is why we have a pyramid in terms of trophic levels. All right. So basically, this is a real nice sheet. I want you to make sure you got a good handle on this. Then I'm going to show you a sample problem that will wrap up this video. The loss every time I change an energy form, all right, you're assimilating energy that they consume. In other words, you're changing the form of energy from chemical energy, all right, to energy I can use in ATP, all right. As energy passes from one organism to another, from prey to predator, the amount of useful energy decreases. Remember, we've had those terms, usable energy and non-usable energy. The rule of thumb is about 10% of the energy level on any trophic level is assimilated by the next trophic level, although this number is often much lower. This is called the trophic level efficiency. And I'll show this in just a second. Consequently, the biomass that can be supported by primary producers declines at each trophic level up the chain. So in other words, if I start, here's the first, this is level 1. All right. As I go up to the second level, all right, the rule of thumb is about 10% of the energy is assimilated by the next trophic level. So basically only about 10%, level 2 has 10%, all right, of the energy that was available on level 1, which basically means when I go from level 1 to level 2, all right, in terms of usable energy, the usable energy decreases, all right, by 90%, which is, if you think about that, it's just staggering how much energy is lost as you go up the chain. All right. So as you go up, as you go from level 1 to level 2, you have a 90% energy loss. As you go from level 2 to level 3, the same thing. You're going to lose 90% of the usable energy. All right. Sorry for the abbreviation there, but I think you get the point. You're going to lose. I hope you do anyway. You're going to lose. That's why you have this narrowing effect. That's why you have a food pyramid as you go up. So that's why we form this what's called pyramid of biomass. And this is kind of interesting the way they put it. This explains the pyramid of biomass. That's a common feature of the ecosystem structure. This is a really interesting way. I've never seen this described this way before, but to put this another way, it takes far more land to support a top predator than it does to support an herbivore. So remember, the herbivores are going to be on level 2. Remember, they're eating the photosynthesize. They're only eating herbs, so they're basically eating the green plants. But the amount of land, all right, is going to be, there's going to be more food available for the land, whereas the predator up top here is going to have less food available, which explains why there's not too many apex predators. All right, take a look at this. Oh, let me show you one other problem here. I'll show you a sample problem that you could run into. All right, this shows here. I just want to focus on number one. Let me make this a little bit bigger for you. And basically, it'll say here the net. You can see this is a simplified equation for photosynthesis. You start with carbon dioxide and water and form carbos and oxygen. This is a short equation for respiration, almost the reverse of that. You start with carbos and oxygen and make CO2 and water, and also over here, of course, would be ATP, adenosine triphosphate. All right. Now, ATP with it. And this just shows an example, NPP equals GPP minus the respiration. So here's an example here, the net primary productivity, all right, there's your NPP, all right, of a particular wetland ecosystem is found to be 8,000 kilocalories per square meter. If respiration by the aquatic producers is 12,000 kilocalories per square meter per year, what is the gravity? That would be the GPP for this system in kilocalories per meter squared per year. And this is really a pretty easy math problem. There's your equation. All right. You just kind of move the GPP minus respiration gives you NPP. You plug in 8,000 for the NPP. You plug in 12,000 for the respiration. By adding 12,000 each side, your X, which is your gross primary productivity, turns out to be 20,000 kilocalories per square meter per year. So, all right, thank you very much.